This is chapter 3, in which we would like to cover the syntax and semantics. So this chapter is about describing syntax and semantics. This chapter is going to be divided into two videos so that we can cover the whole topic. First, I would like to start define what a grammar is in computer programming language context. We know what grammar means in English language or Arabic language, because the grammar are rules of the language. Usually when you talk about a grammar, you talk about the rules that governs the use of the language. In programming language, grammars is something to do with the expressions and programming rules. So generally, grammars are the language of the language. That means it's the rules that define the language. And behind every language, there is a grammar that determines the structure of the language. So this chapter explains the programming language grammar notations, and would like to use some notation like BNF, Backus Naur form, and also extended Backus Naur form, and the regular extension to BNF. So first, let us make a distinction between two important terms, which is syntax and semantics. There might be some interuse or some mixture or some confusion between the two terms. The syntax means the form of a structure of the expression or statements and program units. So the structure of the expressions and statements in the program unit is called syntax. But the meaning of these expressions and the meaning of these statements and program units is referred to as semantics. Both semantics and syntax provide the definition for the language. So the language definition is the marriage between syntax and semantics, which is the structure of the expression and their meaning. Who use these definitions? Who use these such definitions? These definitions, this kind of definitions of syntax and semantics, are used by language designers, by implementers, by those programmers who design applications using this language. So they have to understand these kind of definitions. There is some terminology that we need to understand, which is like sentence. What is a sentence, and what is a language, and what is a lexeme and a token in programming context. A sentence is a string of characters over some alphabets, just like a sentence in English language. And a language itself is a set of sentences. So a group of sentences make a language. A lexeme is the lower level syntactic unit of the language. The lower level unit means the components of these sentences. Here is like some commands that you have in some programming language, or some identifiers like begin, start, end, execute, and so forth, or like some operators. These are the syntactic units, that means components of such expressions. And a token is a category of lexemes, like identifiers, for example, functions, procedures. All these components of the language category is called token. Also, there is some terms that we need to explain, which is recognizers versus generators. Recognizers, this is a formal definition of the language. Recognizers means a recognition device reads an input, like an input device reads an input string over the alphabets of the language and decides whether the input string belongs to the language or not. So in compilation process, there is some application called recognizers. These try to recognize these kind of alphabets and try to decide whether these strings belong to the language or not. Like compilers, for example, as I said. So these recognizers, they will tell the compiler whether to continue processing this language or not. Like syntax analysis part of the compiler, for example, that decides whether the compiler should go ahead with these expressions and execute them for further processing for the next step. And generators, this is a device that generates sentences of a language and determine if this syntax is correct or not. How these generators decide whether this part of the sentence generated by the recognizers or accepted by recognizers are correct or not, they do that by comparing them to the structure of the generator. So the comparison, this comparison of the parts of the expressions accepted by the recognizers and compared by the generators is kind of deciding whether this language contains syntax error or not. So generators will actually work after recognizers to decide on the correctness of such expressions. Let us talk about context-free grammars. The context-free grammars, or CFG, it is the short name of CFG, and this is a common name in studying programming language using BNF, Backus Naur form. What is a context-free grammar? Context-free grammars developed by Noam Chomsky in the mid-1950s, and actually is being implemented 8 years later in ALGOL after the development of ALGOL language. So the language generators meant to describe the syntax of the natural language. So they use the natural language to create some generators to describe them. So it's actually kind of not very technical when it is being developed. It's like a pseudocode for the generators to decide on the formal language. It is called context-free language at that time, but Backus Naur form 1959, which is invented by John Backus to describe this syntax of ALGOL 58. This is the first language to be subjected to this context-free grammar to test the expressions. So BNF is kind of equivalent to context-free grammar that has been developed in the early 1950s. What are the fundamentals of BNF? In BNF, Backus Naur form, abstractions are used to represent classes of syntactic structures. So they act like variables, and we call them non-terminal symbols or just terminals. And these terminals are representing lexemes or tokens, which are the identifiers, the functions, the methods later in a formal programming, high-level programming language that, as we will see later. And they have a rule. This rule has a left-hand side, which is called LHS, which is non-terminal, and right-hand side, which is RHS. This could be terminal or could be non-terminal, as we will see in some examples coming up here. Like non-terminal, for example, enclosed in angle bracket. This is the angle bracket here. The angle bracket is like a less than and closed with a greater than. So the identification list will be here, or the statement is going to be here between the opening angle bracket and closing angle bracket, that determine the identifier, or determine the identifier and the identifier list as well. So kind of like a recursion here. So if statement, for example, is being explained like this. So this is if statement, if logic expression, then statements. If, and then the logic expression. That means if the logic expression is true, then a statement following the if, following the true, evaluation of the if logic. And there is a finite non-empty set of rules, so it could go on and on and on in the recursion format. There is a start symbol. Start symbol is a special element of the non-terminal of this grammar, and for example, this start symbol will means expand into, or determines, or imply, as in the English language. So the noun phrase that mean may expand into article noun, that if we were describing a programming language, we could say something like this: expression may expand into expression plus expression. So expression might extend, might expand, like expand into more than one expression, two expressions, and we can use operators like this. So our expression can be divided into more than one expression, like expression plus expression. But we use term like this right arrow, that means expand into. Instead of using the word expand into, they use this right hand or right side arrow. So if we are working with grammars as mathematical objects, then instead of using this may expand into, we could simply write this arrow. Like this expression could be rephrased like this: expression, and then this symbol, which is the thick right arrow, that means may expand into or determine expression plus expression. And this could be repeated in terms of what we call recursion, as Chomsky explains. He said linguistic recursion as something that occurs when grammatical sentence, which include a noun or noun phrase and verb, might or might not contain another sentence. But if it contains another sentence, this sentence itself could expand into another sentence, and so forth. So a small noun could make a phrase. A small noun could make a phrase, a big phrase, and each noun in this phrase could be expanded into other phrases, making such phrase more expanded. So in programming, recursion is a useful technique for specifying and processing complex data structures, as in Chomsky understanding, when he said there is no upper bound or outer limit on how many sentences can be maintained within each other. So it is opened for unlimited number of sentences that could be derived from one sentence. This is what is called recursion in the language. I would like to show you how we can actually describe list using syntactic list as using recursion. For example, in describing list, syntactic list are described using recursion using this notation, like identification list implies identification list, or this is or identification, and then anything between angle bracket may be expanded to something else. So this is set free, but this one could be expanded. So we can actually start expanding this one, and every time we see this angle bracket may expand again to another set of expressions in which there might be another angle bracket, and so on, in terms of recursion. And this is called a derivation. Derivation simply is a repeated application of rules starting with the star symbol and ending with a sentence. This sentence could be the last output or the result of this derivation. For example, if you look at this example, which is this is a classic unambiguous expression grammar. If you look at the expression here, that means expression can determine two things. Can determine term plus expression. So the expression may expand into term plus expression. Good. Now leave term, take expression. Take this one. Expression may expand into term by itself, and that means expression could mean term plus expression, or expression also could mean just term. Take the term. The term can expand into term multiplied by factor. That means the term itself can equal or imply or determines or expand into term multiplied by factor. Again, term could mean only just factor. Could mean factor, just factor. A factor could mean or can expand into expression between two parentheses. And a factor also could be expanded into constant. A constant like any constant, like 7, like 3. So could be a number, just constant. A constant could be a number, of course, or a letter. Here they said a constant could expand into an integer. Integer, that's it. It's like the last result of this grammar result, which is an integer, like 7. I'm going to give you a rule here. Like, for example, how do we know that, for example, this 3 multiplied by 7 is a valid expression? If we'd like to use our example to prove that 3 multiplied by 7 is actually a valid expression, we can take it step by step. Like, for example, expression may expand into term. Okay, expression may expand. How do we know that expression expand into term? Because if I go there, expression, this one here, he said expression may expand into term. Expression here, this is the second one. Expression may expand into term, and so on. Take the second one, which that means this term may expand into term multiplied by a factor. And term might be term multiplied by a factor. Here, like this one, term equal term multiplied by a factor. Third one here. So that means this term might be factor multiplied by factor. Why factor multiplied by factor? Because term could mean a factor. How do we know that a term could mean a factor? These two are equivalent, because here said a term could mean a factor A term could give me a factor. So here, factor multiplied by factor, because I was just substituting this term by factor. It could be a constant multiplied by factor. Why constant? Because a factor could be a constant. How factor could be a constant? Because a factor could be a constant from here. Factor equal to the constant, this one here. And then a constant could, and this one might expand into constant multiplied by constant. Why I replace this factor by constant? Same as like I did before. A factor could be a constant, so I replace this factor by constant. So constant multiplied by constant, which could be 3 multiplied by constant. Why? Because a constant could be an integer. How do I know that? Because here a constant could be an integer, the last one here. So this one, 3 multiplied by constant, and then constant, since a constant could be an integer, this I can replace the last one also with 7. So the last one is actually 3 multiplied by 7. Now I was able to prove that 3 multiplied by 7 using this grammar is actually a valid expression. So this is how we can actually try to provide such examples, and every example that we talk about expression, guys. When we talk about expression, we talk about the second part of the equation. When, for example, here, if I would like to write something here, for example, y equal 6 plus c. This is an equation, right? This is an equation because it has an equal sign. But what is the expression? The expression is this part. This is the expression. So we remove this part and we leave this one. This is the expression. So when we talk about expression, we talk about the right hand side of the equation. So here 3 multiplied by 7 is an expression, which means that an expression simply, guys, is a combination of operands and operators, such that the operands could be constants and operators are these mathematical operators like multiplication and division, subtractions. This example here is multiplication, for example. So derivations. In derivations, every string of symbol is derivation is a syntactical form. That means it is part of the syntax of the syntax itself. So a sentence is a sentential form that has only terminal symbols. Terminal symbol means the symbol that we use in the expression. So a leftmost derivation is the one in which the left non-terminal in each essential form is the one that is expanded. That means here the one on the left is the one that expanded. This one, everyone in the left is the one that expanded to the one on the right. That's why you see on the left hand side is only one single term or unit, while on the right hand side you could see expression, or you could see expression like the first one here and the third one, or you could see only one element. It could be an element or could be operands with operators. So the derivation may be neither leftmost nor rightmost, because it could end at any time with only a single unit. This is an example of grammar. Like a program is a group of statements. Okay, a program is a group of statements. This group of statements is a statement or statement. It could be statement or more than one statement with an S, statements. And one statement could be expanded into variables which equal to expressions. Variables could be constants like A or B or C or D. This bar here means or. It could be any one of these. Expression could be expanded into term plus term or here term minus term. That means it could be for example 2 plus 4, or it could be 2 minus 4. It could be any one of these are valid if we would like to apply them to this example, for example. And a term might be expanded to variable or constant. So it could be a variable or constant. We know the difference between variable and constant. So a variable is something that changes through program processing. A constant is a value that is actually a fixed value. So in this example, a program could lead to statements, and statements could be one statement, and that statement could be variable and equal to expressions, and this expression could be constant a equal expression, or a constant a could be equal term plus expression, because expression is actually a term plus expression as well. And also this term could be var here. Variable could be var, could be expression, or could be term. So here we can say that a equal var plus term. And since this variable could be a constant, it could be b, because here it could be a or b or c or d according to this example. Var variable could be one of them, so I'm just using b here. Plus what? Plus term. So put term here, and this term could be a constant. A term could be a constant because here term could be either a variable or a constant. So if you use a constant, then he can use it here. A equal b plus constant. So a valid statement like that could be like this. A equal 7 plus 3. So this is a valid expression under this rule that we used right here. If we would like to represent this rule or grammar into parse tree, a parse tree symbol is a hierarchical representation of a derivation. So it is a hierarchy that explains the representation of this derivation. It is the same as this one: program, statements, determine statement or statements. And a statement could be a variable which lead to an expression, and a variable could be one of these constants, and so on. But I'm just using it in a tree, in a hierarchical tree, which is program lead to statements. Statements could lead to statement, and that statement could be like this one, like the whole thing: variable equal expression. This variable equal expression. I'm just putting these hands to put to show that the statement is actually could be represented like this. Could be represented like variable equal expression. Since variable could be a, then I can put a here equivalent to variable, and this expression could be expanded into term plus term, term plus term. As in the rule, and this term could be a variable. So, and this term could be a constant. Look at the equal sign here, still there. This is the plus sign, still here. This equal is variable equal expression, so leave equal here. And this this expression expanded into term plus expression, so leave the plus here. But come here to this term. Term could be a variable, and a variable could be b, and term could be a constant. So if you represent this in a tree like that, this is called parse tree. It is like a chart that represents the grammar. The term ambiguity in grammars, a grammar could be ambiguous. So a grammar is ambiguous if it generates sentential form that has two or more distinct Parse trees. like this example here. If you look at this, this is actually, it's called ambiguous expression grammar. If you look at this rule here, this grammar, expression expanded into expression, operation, expression or constant, and operation could be division or could be subtraction. This operator or operation or operator. So expression is expression, operator, expression or constant. That means this one is being explained here, like operator could be a division symbol or could be a minus. As I said, this bar means or and constant. If we would like to represent this one, look at it. I can represent it into two different ways. Look at both these parse trees. Expression here, expression lead to or implied expression, operator, expression or constant, right? Okay, good. So here I can say expression could be expression, operator or expression, which is the same one here. I didn't do anything different until here they are the same. This expression could be expression of the expression, which is the same thing. I'm just repeating it here. Since expression could be expanded into expression, operator, expression, then I can just put it here for that expression, okay? And I do the same here on this right hand side. On this one I took the left hand side, but on this one I used right hand side, and I repeated this expression right here. Okay, expression could be a constant because here it could be this one or just a constant, right? So okay, so expression could be a constant. So draw a line down there for expression, for this expression and this expression, and put constant, and do the same for this. So here I'm going to also use one line here for this. So this one, expression is a constant, expression is a constant. For these operators, here they use minus, and here they use minus, and here we use division, and here they use division. Look at the last line, the last statement. Constant minus constant divided by constant, and here constant minus constant divided by constant. They are typical. And in this case, let me go back to my definition. They said a grammar is ambiguous if and only if it generates a sentential form that has two or more distinct parse trees. So the same rule generates these distinct parse trees, because I could work it differently and come out with the same result as in this example. So this is what we call an ambiguous expression grammar. An unambiguous expression grammar, if we use a parse tree to indicate precedence level of the operators, we cannot have ambiguity. Like this example, for example, if this example we use it, we can only generate this parse tree. Expression leads to term minus expression, as in this one. And expression is a term, and a term is a constant. And then also here, this term could be term divided by constant, like this one. Term could be term divided by constant, or a term could be just a constant here. So if the term is a constant, just draw a line here and put constant on these two. This generates an ambiguous expression grammar for this parse tree, and it is unambiguous. When we come to this backwards now form also has an extension format. Is called extended BNF, and in this extended BNF, optional parts are placed in brackets, so you have to have brackets. And in the difference is that you can put brackets like this, and whatever you put between these brackets, that will be optional. So for example, procedure call could indicate or could imply identification, and this is expression list, which is between two parentheses. Here they put like parameters or arguments. So in this example, simply they would like to tell you that a function could be called with or without parameter list or arguments list. And alternatively, some parts of the right hand side are placed inside the parentheses and separated through vertical bars. So you can actually have operators like this, plus and minus, separated with this or, and between two parentheses. That means a term could lead to a term plus constant, or you can say a term could lead to term minus constant. So instead of writing two of them, you can just use parentheses and write plus here and minus here, separated by this bar, which is or. Also, another thing in extended Bow's narrow form is the repetition. Expression could be repeated more than one time, and this repetition could always be placed between braces, these braces. So if you actually put something like this, identification imply a letter, and then this letter could be letter or digit, and then if you put between braces like that, this means it is repeated, like in loops, for example. So any expression that is repeated is kind of called EBNF. EBNF means extended Backus Naur form. And some differences in examples between BNF and EBNF using this grammar. For example, expression could lead to expression plus term, or expression minus term, or just term. Any one of them, any one of this, either expression plus term, or expression minus term, or just term. And expression could lead to term multiplied by factor, or term divided by factor, or just factor. If you'd like to use an example of this is Backus Naur form, we have seen similar example of this. But in EBNF, where you can use parentheses and you use braces, here is an example. For example, expression expanded into term, and then plus term or minus term, and this one also could be in a repetition format. The second example is term implied factor multiplied by factor, or factor divided by factor, and also this one between braces. That means it is in actually repetition format, so it could be in a loop format or anything like that. The recent variation in EBNF, like they said, alternative right hand side are put on separate lines. So if you have right hand sides, you can put them in separate lines to make them look different from BNF. Also, some scientists in programming languages, they introduce also a colon or double colon instead of just using this one, because this one is used in BNF. But when people see like double colons here, they understand this is actually not a BNF, it is EBNF. Also, they used opt for optional part. If there is opt optional part, that means this is optional part. They use it in EBNF as the term. And also they use one off for choices. So if there is some choices or options, they use one off as a term to indicate that this is actually a choice, just to make it different from BNF. In static semantics, static semantics is not about the meaning of the grammar, because uh, context-free grammar cannot describe all of the syntax of programming languages. It describes most of it, but not all of it. So some context-free grammar, like for example types of operands in expressions, and there is some non-context-free grammar like variables that must be declared before they are used. Such rules like that in some programming languages. Some languages they cannot allow the use of any variables if you don't declare them. Some programming languages they don't allow declaration of variables in the middle of the program. They have to be declared in the head of the program, and so forth. So the syntactic meaning is simply is not about the usage of these grammar rules. So they actually depend on the usage of this type of operands in expressions. Operands are the component of expressions together with operators. So it depends on the programming language that you are using these CFGs. The attribute grammars, or they call AGS or EGs, have additions to context-free grammars to carry some semantic information on parse tree nodes. So kind of explaining the nodes on the parse trees, or making some explanation or definition on these parse trees. And the primary rule for these attribute grammars is that static semantics specification is being explained in the program units, and also compiler design static semantic checking. There is some checking for the syntax in the compiler design. So some programming language they have to explain some sort of semantics in checking the syntax of the language. This is attribute grammar definition. So an attribute grammar is a context-free grammar with some additions. Like they can, for example, use some sort of symbols like this. For example, for each grammar symbol X, there is a set of AX, such that A is attribute grammar of attribute values. So A between two parentheses X. So each rule here has a set of some function that defines some attributes, and each rule has some set of predicates to check its consistency. So they use some symbols, letters, parentheses to explain such syntax. So also they can use something like this, like x0 imply x1 until xn, such that x1 is the start and xn is the last. They can use such kind of definition like this to be a rule. Or for example, they use functions of this format, s x0, such that for example s is a function equal f a x1. That means here, for example, this is an argument of this function, and the whole thing between the two parentheses here is actually an argument for the outer function, and so forth. This define synthesized attributes, or what is called synthesized attributes, which is explanation of the complication of these expressions. So if you have function of this format, for example, they can use this kind of expression to define inherited attributes, such that an attribute of a function can be inherited by another function, and so forth. So simply, there is some definitions using symbols, using characters, using operators, using some relational operators, or using some assignment operators, numbers, digits, simply to explain such kind of attribute grammar in the context of expressions or identifiers, or even function calling. So an example here for this attribute grammars, like for example, assignment statement is equal to variable which lead to expression. Expression imply variable plus variable or variable. A variable could be A or B or C. So the actual type for this synthesized for variable and expression. Variable and expression, you are talking about two things: variable here and expression. And then in the end, this one, it is identified. Each one is identified by its own expression on the right hand side of this arrow. So something like that. For example, here in this part, this one could be either A or B or C. Implied, this one could be here, like that, could lead to A or B or C as constants. In the next video, I will cover from this slide onwards.